So thank you to the organizers for inviting me to this PQC forum, and I'll be talking about algorithms for lattice problems via discrete Gaussian. Uh, so, so this is basically the current fastest theoretical algorithm for solving these lattice problems. Okay, so what is a lattice? We have already seen quite a bit about this. So lattice is a set of points that is spanned by n vectors v1 to vn, which we call the basis vectors. So it's a integer combination, all integer combinations of these n vectors v1 to vn. And so here's a picture of a two-dimensional lattice where v1 and v2 is the basis, and we can, as you can see, all integer combinations are in the lattice. And one of the most fundamental problems in lattices is the shortest vector problem, where the task is you're given a lattice and you want to find the shortest non-zero vector in the lattice. So, I mean, so this, for example, here's a lattice with these two are the basis vectors, and this is the shortest vector. And so this problem, I mean, is easy in 2 dimensions, but it becomes hard in n dimensions. In particular, the best known algorithms for solving it run in time 2 to the O of n. Okay. And then I'll be talking about the closest vector problem. So the closest vector problem is another fundamental problem where you are given a lattice and a target vector t. So you have some you have some vector t, which is the target, and you want to find the closest vector to the target. Okay. And the basis of a lattice is not necessarily unique. For example, here's a lattice where the basis v1 and v2, and v1 prime and v2 prime is another basis of the same lattice. And this is part of the reason why these problems are hard, because if you see a basis which is bad like this, it seems difficult to find the shortest vector, and when it's something like this in n dimensions, it is generally very hard. But when you have a basis which is relatively orthogonal, it's much easier to see the shortest vector. So, okay. So one of the first results in computer science on lattices was the Lenstra-Lovász algorithm. So this was an efficient algorithm that outputs a somewhat short vector in a lattice, and it has several applications which include solving integer programs in a fixed dimension, factoring polynomials over rationals, finding integer relations like this, and also a lot of cryptanalytic applications like solving some variants of RSA and so on. Okay. Lattices began to be used to create crypto systems, starting with the breakthrough result of ITI in 1996. And since then, I mean, basically, there have been several crypto systems based on lattices. So cryptography based on lattices has many advantages compared with traditional crypto systems like RSA. So first of all, it has security, which is based on worst case hard problems, and we believe that it is resistant to quantum computers. And in some cases, these algorithms are much faster. The encryption decryption algorithms are much faster than the traditional RSA type algorithms. And also we can do potentially much more. For example, we can do fully homomorphic encryption and so on. This is a small list of lattice-based primitives that have been constructed. In the past, this is not an exhaustive list. I've just listed some examples. For example, public key encryption. There are several candidates. Then CCA secure public key encryption, identity-based encryption, oblivious transfer, circular secure encryption, hierarchical IBE, fully homomorphic encryption, and so on. I mean, there are plenty of examples of what have been constructed using lattices. Okay. And here's so far the progress on provable SVP algorithms. So it started with, so the first major algorithm was what was mentioned in the previous talk also. This was by Kannan. It is a algorithm that ran in time n to the O of n. And then after like 15 years, there was a result by Aitai Kumar and Sivakumar that gave a 2 to the O of n algorithm. for solving SVP. This was a sieving algorithm. And then there was a series of results that tried to improve the exponent. So so the best exponent for the sieving algorithms was 2 to the 2.465 n. And then Micciancio and Vulgaris came up with a deterministic algorithm that ran in time 4 to the n, and this was basically the state of art until our result, basically, which gives a 2 to the n algorithm, and it is arguably even simpler than the previous algorithm. So okay, here's the progress on CVP algorithms. So again, the CVP, the first algorithm was by Kannan in 86, which was n to the O of n, and then there was basically no progress on CVP. I mean, solving exact CVP, at least for a long time, until Micciancio and Vulgaris came up with this 4 to the n algorithm. And then in this talk, we show that this can be also done in 2 to the n time. Okay. So I'll be talking more about the SVP algorithm, since it's much simpler compared to the CVP. The approximate CVP algorithm can essentially be obtained using a similar idea. I'll briefly mention it at the end. And then the exact CVP algorithm requires much more work. Our CVP algorithm actually computes all closest vectors, and so is in some sense optimal. In fact, I mean, if we want to compute all closest vectors, then we cannot hope to do it better than time 2 to the n. So it is in some sense an optimal algorithm for solving this problem. Okay. So here's a brief talk outline. I'll be first talking about what is a discrete Gaussian distribution, and then I'll show that obtaining discrete Gaussian samples for an appropriately small standard deviation S implies a solution to the shortest vector problem. Then the main result would be how to obtain the discrete Gaussian samples for a small enough standard deviation S. And I'll end with a summary and some open questions. Okay, so here's what a discrete Gaussian distribution is. So consider this function, which is which is the Gaussian function, which is rho of x is e to the minus pi x norm x squared by s squared, where s is roughly the standard deviation, and the probability that this random variable x takes the value x is this rho s of x divided by rho s of L, where by rho s of L I mean the Gaussian function summed over all lattice vectors. So it's sigma rho of x summed over all x in the lattice. And here's a picture of how the Gaussian function looks on a two-dimensional lattice. So notice that it is more as you go closer to the origin, and as you go farther from the origin, the mass decreases. So this is the discrete Gaussian distribution, as I mentioned, and what was known was that it is easy that there are efficient algorithms, for example, Gentry-Picot-Vaikunthanathan algorithm, that obtain discrete Gaussian samples for a large standard deviation. And notice that for very small standard deviation, so the mass is concentrated on the zero. So the distribution is highly concentrated on the zero vector. So for example, if s tends to 0, then the entire mass is on the zero vector, right? And for very large s, the distribution is quite well spread out, and this is what they used in this result to try to obtain discrete Gaussian samples for large parameters. So the question, this brings us to the question whether we can find an optimal standard deviation for which the distribution hits the shortest vector with good probability. Okay, so now I'll basically show why we can get a solution to the SVP if we get discrete Gaussian samples for a small enough parameter S. So we know from estimates from the results from a result on sphere packing by Kabatiansky and Levenstein that the number of lattice vectors of length at most r times lambda 1 L is upper bounded by this number 2 to the 0.401 n times r to the n. So we can assume that the shortest vector is of length 1 without loss of generality, and we can upper bound uh, this rho s of L by 1 plus polynomial 1 plus basically poly n times the largest value of the Gauss the this is the number of vectors at radius r times the Gaussian mass at radius r, which is e to the minus pi r squared by s squared. This is because basically the Gaussian mass will be only significant for I mean, you can think of a shell at radius r, and the Gaussian mass at that for that shell is precisely this, and then only polynomially many of these shells would matter. So we can upper bound this Gaussian mass of the lattice by 1 plus poly n times the maximum of this number, and then an easy calculation shows that basically if you do we can show that the probability that the length of this Gaussian mass for the length of x is equal to lambda 1 L, the probability of this can be lower bounded by 1.38 to the minus n, basically by using the upper bound on the denominator. We can show that this probability can be lower bounded by 1.38 to the n minus n. What this means is that if we have more than 1.38 to the n samples at this particular standard deviation, then we'll get the shortest vector with good probability. And okay, so what we'll do is we'll basically try to obtain that many samples for the appropriate standard deviation. Okay, so how do we obtain discrete Gaussian samples for small parameters? So our goal will be to take samples of large width s and then output samples of some smaller width, say s over square root 2. And if we can do this, then we can simply keep on repeating and obtain samples from smaller and smaller standard deviation and ultimately get our desired samples. So here's the first naive attempt. So if let's say we are given x, we output x divided by 2. This looks like it seems like to be from the right distribution, but the problem is that x divided by 2 is not necessarily in the lattice, right? So a second attempt could be that we only take x which are in twice the lattice and then output x divided by 2. So what this means is basically we have samples from the discrete Gaussian at parameter s, and we only keep vectors that are in twice the lattice and then divide by 2. But then notice that the number of vectors that are in 2L are roughly about 1 over 2 to the n fraction of the total number of vectors. And so we will be throwing away all but a 2 to the minus n fraction of the vectors. And so we'll be losing a lot of vectors. And since we hope to do it in a good running time, I mean basically about 2 to the n, I mean losing that many in just one step is kind of bad. So we want to do something better. So a better attempt is to partition the samples according to the cosets mod 2L. So note that there are 2 to the n different cosets mod 2L which look like this. The cosets are 2L plus summation ai vi, where ai's are in 0, 1. So it's basically all the, I mean these are the 2 to the n different cosets spanning looking at different values of ai. So we get these 2 to the n different cosets where v1 to vn are the basis vectors. So what we then do is we then take 2 samples from a coset and output their average. Notice that if there are 2 samples that are in the same coset, then their sum is in 2L, and so their average is still in the lattice, right? So intuitively, since x and y are both Gaussian with parameter s, we expect that x plus y should be Gaussian with parameter s times square root 2. And when we take their average, it should be Gaussian with parameter s divided by square root 2. So x and y are Gaussian, so x plus y should be Gaussian with square root 2 times s parameter. X plus y divided by 2 should be Gaussian with s divided by square root 2. So, but is it actually distributed that way? So this is just an intuitive explanation. So let's see why it is actually distributed that way. So here's a important lemma which shows that if we pick a coset C with probability proportional to the Gaussian mass on that coset, squared, and then output x plus y divided by 2, where x and y are sampled from that coset at parameter s. Then the output distribution is the right distribution that we want, that is this discrete Gaussian from s divided by square root 2. And this the second part is a statement that I will need at the end for the proof, and it's very related, so I just put it here. So the proof of this, I mean, we can do it algebraically, and it's a simple calculation, but the intuition is this. So consider the bijection from the direct sum of two cosets of the same coset, 2l plus c, direct sum 2s plus c, and take the union over all different cosets. And consider this bijection to this set that is given by, so x and y is mapped to x plus y divided by square root 2, comma x minus y divided by square root 2. Notice that if x and y are in the same coset, then x plus y is in twice the lattice, and so x plus y divided by square root 2 is in square root 2 times the lattice, and also x minus y is in twice the lattice, so x minus y divided by 2 is in square root 2 is in square root 2 times the lattice. And it's like easy to see that this is a bijection. Okay, so from this the second part follows almost immediately, because you can take the Gaussian mass of this, and you will get exactly at parameter s, and you will get rho s 2l plus c whole squared, and you take then that should be equal to the Gaussian mass of this, which would be rho s of square root 2l whole squared, but rho s of square root 2l is the same as rho s divided by root 2 times of l. You can just scale both of them by a factor 1 by root 2, and it does not change the Gaussian mass. So this is immediate. And for showing this, basically you need to see that if we take the Gaussian distribution here, so if we pick the coset C with probability proportional to this, that is actually equivalent to picking, and then x and y from the discrete Gaussian in this coset, that is equivalent to picking x and y here, and I mean basically using picking them using the Gaussian mass, and then notice that x plus y divided by 2 is in square root 2 times the lattice, and so we get the correct distribution here, because if we fix x plus y divided by 2, then x minus y divided by 2 spans over the entire lattice, and so the probability we get is proportional to this. And if the probability is proportional to this, then it actually has to be equal to this, because it's a probability distribution and it has to sum to 1. So this was a rough explanation. Of course, we can do a more formal calculation, just algebraically. But what we want, so let me emphasize that we want to pick a coset C with probability proportional to the initial probability squared. Okay, so this reduces our problem to the following. So more generally, what we want is, so we want to bucket the samples into 2 to the n different buckets based on their cosets mod 2l, and then we want to pick a bucket with probability proportional to the square of the original probability, and then output the average of 2 vectors in this bucket, right? So for this, what we will need is a square sampling procedure, which is given samples from a distribution p1, p2 up till pn, we want to output samples from the squared distribution. So which is the output samples from the distribution p1 squared, p2 squared till pn squared divided by summation pi squared. Notice that we do not know the values of pi, so we cannot do it directly. So we want to use the original samples to get these squared samples. So this reduces into this probabilistic question, and here's how we solve it. We solve this using rejection sampling. So given samples from an unknown distribution P, we want to output samples from this squared distribution. So the way to do it is sample I from the original distribution P. So, and then toss a coin with probability Pi divided by P max. So it's heads with probability Pi divided by P max and tails otherwise. So then if the output is heads, we output Pi, and if it is tails, then we ignore. Uh, okay. So the question is then how do we toss these coins with probability pi divided by p max? Uh, we toss these by bucketing the samples and observing the number of samples that fall in bucket I. So this is so basically we bucket the original samples and then observe the number of samples that fall in bucket I, and then we I mean there'll be some problems due to some correlations, but we can use some Poisson machinery to get rid of them. But basic idea is this. So notice that we get the right distribution because we get the sample I. The probability that we get the sample I is proportional to pi times pi divided by p max, which is pi squared divided by p max. So probability that we get the sample I is proportional to pi squared, and so we get the correct distribution. So what is the loss? So by loss I mean how many samples. How many samples do we get if we start with m samples? If we start with m samples, notice that we will be keeping the sample with probability pi times pi divided by p max summed over all I. So from m samples we will get m times summation pi squared divided by p max samples. So this is basically our loss, essentially. Note that a trivial algorithm where we could just just keep if the two match and otherwise we reject, would give us m samples to we get m times summation pi squared samples. So we saved this 1 over p max factor by using this rejection sampling. Okay, so is this loss rate good? So loss rate for one step, so this term could be as small as 2 to the minus n over 2 when p max is 2 to the minus n over 2 and all the other pi's are equal. So in the worst case this could be as bad as 2 to the minus n over 2, and so for 100 steps it could be like something like 2 to the minus 50 n. So this seems problematic because we started with m samples, we get like this small number of samples, and we want to go this take this at least a logarithmic number of steps, log n number of steps. So this does not seem so good. But so here comes the final kind of analysis, which was almost magical because we could not give a good reason why this happens, but it was luckily so that when you do the calculation for the loss rate for our particular distribution from s to s divided by square root 2, the loss rate is this. So it's basically the squared probability summed over all cosets divided by the probability of the largest coset, p max, and the largest coset is the central coset, so it's rho 2l divided by rho l. And using the lemma that I mentioned earlier, we can simplify this whole thing to rho s divided by square root 2l squared divided by rho sl and rho s divided by 2l. And when we write this whole product and we telescope, we see that almost all the terms cancel. Basically, the numerator cancels with one term on the left side and one on the right side, and so almost all the terms cancel, and what we are left with is this basically rho s divided by square root 2l divided by rho sl times so the rho s final is the last standard deviation, so rho s final l divided by, and this is easy to lower bound by 2 to the minus n over 2 using standard estimates from lattices. So what we get is that the final loss is 2 to the minus n over 2, which means that if we start with 2 to the n samples from the discrete Gaussian for a large parameter s, then we can end up with 2 to the n over 2 samples from for any required standard deviation. I should say s prime here, something s final basically. So we can start with 2 to the n samples from a large distribution, which we can do efficiently. And then we can get, using this our algorithm, that square root 2 to the n samples for small parameter s. And remember that we needed only 1.38 to the n samples, and so we have clearly more than that. So we have enough to solve SVP. So I'll summarize with some open questions. I'll give a summary. So we started with in time 2 to the n, we are able to sample from the discrete Gaussian distribution of any standard deviation s of any radius. This implies a 2 to the n algorithm for solving SVP. I am missing a plus little o of n term, but it's almost 2 to the n. So similarly, we can sample from the discrete Gaussian distribution over L minus t to find the closest vector to t. So we can use a similar idea to sample from the discrete Gaussian for a coset L minus t, and this results in an approximation algorithm for the closest vector, and then we can use that to find the exact algorithm. A close inspection. So basically, the analysis is not exactly the same for the L minus t, because the troublesome part is that the maximum coefficient for L minus t is not the central coefficient, and so this required more work to show that actually the loss rate is still good enough for this thing, right? So a close inspection of the algorithm shows that square root 2 to the n should be the right answer. So for our SVP algorithm, I mean, we believe that we can improve the it could be possible to improve this algorithm to square root 2 to the n. So far, we have not managed to do it, but what we could show is that we can get a square root 2 to the n algorithm for approximate gap SVP. So the approximate version, so O of 1 approximation for the decision problem. So it is open whether we can turn this into an exact algorithm for solving the exact problem. And I'd be happy to take questions. So for I did not try to implement it, because for implementation, clearly there are other algorithms that work better. I mean, basically, even so, there are other, for example, this sieving algorithms that run faster in practice. I mean, basically. But they're probably not worst case, because they only have a heuristic analysis, so it's not a provable analysis. But so it's probably not so beneficial to try to implement it and see if it's faster. I don't expect it to. No, it's a theoretical algorithm, but it's theoretically, like, there's no provable algorithm that beats this in terms of running time.
Any other comments or questions?
Actually, I couldn't understand how to use Gaussian samplings to solve SVP. Could you explain this part again?
Sure.
The ideas?
So, okay, let me just try to go back a little bit. Okay, so here's what I said. So, okay, so we know that, I mean, there's an algorithm by Gentry, Vaikunthanathan, that gave algorithm for solving the discrete Gaussian for large parameters. And what we want to know is, so the question is, how can we use this discrete Gaussian to solve SVP, right? Okay, so probably no, this is not the right. Right. So we know that if we okay, so what we do is we use this estimates from this result on sphere packing, which shows that we can upper bound the number of lattice vectors by 2 to the 0.401 n times r to the n, right? And now the Gaussian mass on the shortest vector is basically the row of this 1. Basically, so assume that so we can scale the lattice, so we can assume that the shortest vector has length 1, right? So the Gaussian mass on the shortest vector is basically row of 1, which is e to the minus pi by s squared, divided by the Gaussian mass on the entire lattice, right? So I mean, so if we can upper bound this thing, then we can lower bound the probability that the shortest vector, so that x is equal to the shortest vector. The length of x is equal to the shortest vector. Make sense? So what we are trying to do is we are trying to lower bound the probability that we get the shortest vector. We can do that by upper bounding the denominator, which is the row of L. And this upper bound is basically 1 plus, so this is the, at radius r, the Gaussian mass is this times e to the minus pi r squared by s squared. And I mean, this, you can think of it as like a shell at radius r, which has a mass which is a Gaussian mass this much, and only polynomially many of these shells would contribute to the sum, because the rest would be almost zero. So we can bound the rho of L by 1 plus polynomial n times the largest value of this, and so we can bound the Gaussian mass of the shortest vector by rho of 1 divided by this, lower bound this, and for the right optimization we get that the Gaussian mass of the shortest vector is lower bounded by 1.38 to the minus n. This is the probability. So what this means is that if we have these many 1.38 to the n different samples from the discrete Gaussian for our right choice of standard deviation, then we will get the shortest vector with good probability.
You randomly chose. You random chose with this.
So we have a procedure that outputs discrete Gaussian samples, and this procedure basically samples from discrete Gaussian. I mean, if we get independent different samples at this parameter c divided by square root n, then if we have that many samples, then of course we'll get the shortest vector with good probability.
Thanks. Okay.
Sure. What is it? Oh, it's the same question.
Similar question.
Oh, can you say a bit more about the algorithm for approx SVP? Oh, okay. So an algorithm, I mean, for approx SVP, what we did was, it was not really an algorithm for approx SVP, but an algorithm for the gap SVP, the decision version of approx SVP. So what we did was we did discrete Gaussian sampling, but it was above the smoothing parameter, and for this, we showed that if we can get discrete Gaussian samples at roughly the smoothing parameter of the lattice, then this implies a solution to the gap SVP problem. And this equivalence is probably, it will take a while to explain, but how do we obtain samples from this discrete Gaussian above the smoothing parameter? We can do it faster, because there, instead of going from L, so we looked at cosets of 2L, right, in the lattice. So we went from we looked at this 2 to the n different cosets, and if we look at an intermediate lattice between L and 2L, so something like which has, let's say, half of the coefficients are twice the, so we look at an L prime, and we look at the cosets of L prime mod L. So sorry, the cosets mod L prime, where L prime is somehow in between L and 2L. So we consider a tower of lattices, and we make progress. We make slow progress, and we can do this above the smoothing parameter, and this leads to basically square root 2 to the n different samples. So we can basically use a similar idea to start with. We start with square root 2 to the n different samples at a large standard deviation, and we can get it down to the smoothing parameter. And this results in the algorithm for solving the shortest vector problem.
There's another online question.
Okay. Can you sample from DLS for arbitrary S? How does the complexity depend on S? So the complexity actually does not depend on S. So we can sample from arbitrary S, and the complexity is 2 to the n still. 2 to the n plus little o of n. So it does not depend on S, because we need that many samples just to start.
No more questions? Well, then let's thank the speaker.
Okay.